This video is about how one can use projectile motion in Python and matplotlib, and also about some probability distributions that can be used to generate this kind of scene. It's not so much about making it look realistic, but so this is representing 3,000 archers firing towards us from a distance of say 100 meters. All these arrows are generated using the equation of motion, and it looks like this for the motion in the horizontal x direction and the vertical y direction. In Python it looks like this. There's velocity u, and theta is the angle of the projectile in radians. Think unit circle. So 0 or 2 pi is straight to the right, pi divided by 2 is straight up, and pi is straight left. And here it's set to pi divided by 4, which means that it's going to go at an angle of 45 degrees. And here is time in flight, which is how long the projectile will be in the air given the velocity theta and gravity. If it's set to 4, it means that the projectile will hit the ground at the same height as it was fired from. So if one sets it to 2, it will not reach all the way down, and if one sets it to 6, it will go below the height it was fired from. Since I needed to understand these, and I'm bad at math and physics, I spent hours looking at this. And one mistake I did was to think that since this output is in vector, because t is a vector, I thought this part looks like some sinus wave. But it does not. It's just a straight line up in the air with some angle theta, because theta is just a single number. It's not an array. And the second part, minus half gt squared, is how height changes due to free fall, and it decreases more and more. I'll show this in a picture. So when these two are added, one gets a projectile. Next step is to generate many of these projectiles and to distribute their thetas using a normal distribution. The distribution here is mean or log pi divided by 2 and variance or scale pi divided by 4, given in radians. And this is what it looks like with scale set to pi divided by 4, which is way too broad because of the outliers. And here with scale set to pi divided by 12. It's really just a way to visualize the normal distribution. Most arrows fly close to straight up and a few deviate. I forgot to mention that this video doesn't include a lesson on how to set up the animation with the animation looping classes, arrows hitting the ground, etc. to actually generate this scene. And in one place the scipy stats library and its normal distribution is used instead of the numpy one I showed. But I might make a bigger follow-up video on that. As one can see, all these arrows are fired at the exact same time. So how could some delay be added to some arrows so that it looks more like this? And one might think to do this one could use a Poisson distribution. And it is possible, but the Poisson distribution is pretty limited. It just has a single parameter lambda, or the rate or mean. And the problem is that it's defined such that the mean is equal to the variance. So if I set the mean to be say 1, like here, the variance will also be 1. And the problem is that one cannot maintain this nice shape if one wants more numbers on the x-axis. Like multiplying it like this will not help. It's still possible to get it to work with some modifications though. But one distribution which gives a little more flexibility is the beta distribution. Its probability density function looks like this for alpha equals 2 and beta equals 5, and the mean or log set to 0. And these parameters can be tuned to control the shape of this PDF. One thing is that one could think that the mean should be under the hump, but it actually gives the starting point. If one then wants to generate random variates, basically samples from it, here's what it could look like. So this is a histogram. The x-axis is the amount of time in terms of frames that an archer takes to fire off the arrow after a fire command is issued. And the y-axis shows how many archers fire at the different frames. One could also have used the gamma distribution, where the PDF can look like this, or the chi-square distribution. So there are at least 4 ways to do it. Actually 5 if one includes a folded normal distribution, which can also be made to work here. Another topic is how good a whole company is, or specifically how fast the archers in a company are at reloading and issuing their lose commands. Because if one doesn't do something like that, it looks something like this. So here there's 10 companies with 10 archers each, and they always fire with the same company interval, so to say. There are again many ways to fix this, and one way is by using the Dirichlet distribution. It can be called using this nice little line. There are 3 companies, and the first needs more time to reload than the other 2. That's basically what these numbers mean. And if all these numbers are really small, it means that the company with the highest number will be relatively much slower at reloading. And if the numbers are larger, it means the company with the highest number will only be a little bit slower. So it's a way to control the degree of winner takes all. And this last value represents the number of times the companies fire. So it's equal for all companies here, which means that one has to issue more fire orders than what might actually be needed by some companies. But that doesn't matter, it's totally fine if the slowest company issues a loose command at, say, frame 1000, but the animation only lasts for 500 frames. A detail is that the Dirichlet distribution always outputs values in the range 0 to 1, so one also has to scale it. But it's fine, all one has to do is multiply it with some constant and cast it to int. So after this, the reloading time and number of frames is given. This type of hack is quite common in my experience, so take some function which outputs values between 0 and 1, multiply it with a constant and cast it to int. It's good, but it's also obviously reducing data quality, so it's good to be a little bit careful whenever doing this. Another detail, but for sampling many thetas, the folded normal distribution is used, and it's because each company needs to have a theta tied to its x-coordinate. So a company in the middle should have a theta like pi divided by 2, straight up. A company to the left should have a theta more than pi divided by 2, and vice versa to the right. For this implementation, numpy couldn't get the job done, so instead I used the stats normal library to generate theta angles, which are centered on pi divided by 2, and which then decrease toward the edges. This array of values has a preset number of indices, 40, and the company gets a random index 0 to 39, which it then uses to get its theta angle and x-coordinate. And it's done using this so-called percent point function. And what we're looking at here is the x-axis of a folded normal distribution. When scrolling through it, one might think it's a normal distribution. I made that mistake, but these values are actually showing the inverse of the CDF of the normal distribution. They're not showing probabilities, they're showing the theta angles. So most of them are around pi divided by 2, and then they decrease toward the edges of the array. But they never increase. There are no theta angles here that are greater than pi divided by 2, which means that all the thetas are pointing to the right. I'm sure it's possible to fix it in the code, but I didn't figure out how to, so using this code, a post-processing step is needed. After a projectile's x-coordinates have been generated based on the theta angles, an extra function is used to check whether the projectile should move left or right, and then flips the x-coordinates if needed. The plan was originally to calculate the time of survival for someone moving towards the English line at the Battle of Agincourt, but there were too many implementational hiccups like the one I just mentioned. And I also just discovered that flipping the colors might make it look better. Perhaps there will be a follow-up. But also, it's not that easy to simulate time of survival because it depends on the accuracy of the archers and on the armor worn by the person that would be standing here. We don't really know about the accuracy because many archers would probably stand behind a bunch of other archers. So it would take a lot of work to make a study on that. And concerning the armor, just a few years ago, this idea that longbow arrows could penetrate at least well-designed armor from the time was debunked. So there's a lot of uncertainty. But this is 3,000 archers firing 3,000 arrows with a reload time of around 7 seconds. And these numbers would perhaps be something that could be witnessed at one of the most intense moments of the Battle of Agincourt. Modern estimates say there were between 5,000 to 6,000 longbowmen there. 3,000 is still a high number. It's quite unlikely that there would be this many arrows fired on such a small area. And clearly this rate of fire could not be maintained for long because they would get tired and run out of arrows.